Okay, let's continue our program of soil mechanics. So I think the last part of the last video, we have talked about the first part of this chapter number 3. Okay, we are still on this chapter, weight volume relationship. So last time, I think we have talked about all these points from number 1 to number 5, and after that we did one example, one exercise. So in this video, I would like to talk about relative density. So I will take time to explain about this because this is somehow very important for people who are doing modeling in the laboratory. Okay, so I hope you will learn something. Okay, relative density. What is relative density? Okay, point number 6 of this chapter. What is relative density? So this term of relative density is commonly used to indicate the in situ denseness or looseness of granular soil. So the first point you need to be careful is this granular soil. So this is used for granular soil. Please remember that, okay? So sometimes we need to know we need to know how dense is our in situ soil, okay? And if we know the denseness or looseness of our in situ soil, we can decide to improve it, okay? There are many methods of improvement, ground improvement. We will talk about this later, okay? So how do we define a relative density? It's very simple. Relative density is defined by this formula. Do you remember this void ratio? We have talked about this void ratio in the previous video. So if you haven't seen them yet, I recommend you to go and watch the previous video before continue watching this one. Coming back to watch this one, okay? Yeah, but if you know already the definition of void ratio, it's okay. So what is relative density? Relative density is E max minus E divided by E max minus E means. E here is void ratio, please remember, which is volume of void divided by volume of soil particles. Okay, so in this formula of relative density, the dr is, of course, the relative density itself. Okay, relative density given usually as percentage, and the E is the in situ void ratio of soil. This one. Let me use this pointer to make it easy for you. This E is the in situ void ratio, or the actual void ratio your soil have right now. Okay, your soil or your soil sample, the actual void ratio you have. But the E max is void ratio of the soil in the loosest state. It means when the soil is very, very loose, it's not dense at all, then you will get the maximum void ratio. It means, please check look at this formula. E void ratio is volume of void divided by volume of soil. solid particle. So means if this void, the volume of the void is high, the void ratio will be also high. So max E max, big or great void ratio means that the soil has a big portion of its volume is made of void. This is the meaning actually. Okay, so Emax, when the soil is loose, very loose, loosest state. Okay, so I guess that you can immediately guess what is the E mean, which is just the void ratio when the soil is at densest state, when the soil is very, very dense. And the soil is dense, then we get this one minimum. In that case, it means the void, the volume of void is very small in the soil. That's the meaning. Okay. So these are the basic definition of relative density. So this relative density, sometimes it ranges from 0% for loose, very loose soil to 100% for very dense soil. So this is telling you that the more the relative density is high, the more the soil is dense. Okay, so from 0, very loose, to 100%, very dense. But trust me, if you want to achieve 100% of relative density, it's not easy. Okay, so sometimes the engineer are using a qualitative description to classify granular soil by using just this relative density. We can see it in this table. So if the relative density is between 0 to 15, we will say that it very loose. From 15 to 50, it just loose. For example, if your sun has a relative density between 15 and 50, it loose sun. And from 50 to 70, we talk about medium. 70 to 85, it dense. And 85 to 100, it very dense. Okay, so these are just description. So if someone tell you that it dense sand, you can guess immediately the relative density of this sand. Okay, this interval. Okay, in practice, in place of soil, usually have density higher than 20 to 30. Means when you go in city, usually you find this relative density. That density, the relative density is higher than this, 20 to 30. Okay, then you can compact your soil. There are many ways to compact your soil. Make it reduce the volume. If you compact your soil, then the relative density can become greater than approximately 85%, which is very challenging. So it means for you to get your soil to have this relative density, it's very difficult, but people do it. Okay, just by reducing the volume of the soil. So if you reduce the volume of the soil, means actually we are reducing the volume of the void in the soil. So this V will decrease. If the volume of void decrease, it means the soil will become dense. Yeah. Okay. I hope you got it. So I will just keep this formula here, okay? Because we will try to estimate this relative density by using other parameters, okay? So, but remember, the basic formula for relative density is this one, okay? So we can use, instead of using void ratio, like here, we can use porosity also to estimate the relative density, okay? So how do we do that? If you remember, in the previous video, we have talked about this relationship between void ratio and porosity. So we can obtain the void ratio by using porosity with this formula. Void ratio is equal to porosity divided by 1 minus porosity. N is porosity, okay? N, this porosity is N. So it means by using this relationship, E and N, we can obtain the E max. E max will be just N max divided by 1 minus N max. And E minimum will be N minimum divided by 1 minus N minimum, something like that. Because as you can see here, if N is minimum, N is small, the E will be also small. Yeah. So by replacing this formula of E max, we replace it in this formula. And this formula of E minimum, we replace it in the formula of relative density, this E minimum. After doing that, you can obtain the formula of relative density with this by using the porosity. Okay, so in this formula, of course, N max and N min means porosity of the soil in the loosest state and densest condition, respectively. Okay, again, we can use another method to determine the relative density. We have used void ratio, porosity. We can also use dry unit weight, because very often the dry unit weight is what you are dealing with in the lab, you know. So somehow it's sometimes easier to use dry unit weight to estimate the relative density. Okay, so sorry, this is okay, we'll keep it here. So the dry unit weight, as we talked about it before, can be obtained with the weight of soil particles, this solid part of the soil, which is divided by the total volume of the soil. This is the definition of dry unit weight. Okay, and we can use a specific gravity of soil. Means the weight of the soil can be estimated. This dry density can be estimated by using the specific gravity of soil, because we know that the specific gravity of soil is the gamma S, gamma of the soil particle, divided by the unit weight of water. This is definition of a specific gravity of soil. Okay, then we can use this formula as formula of dry unit weight. And then in this formula, if you check, we can obtain the E also. So if you didn't understand this formula, it's okay. But this one is the one we need. This one is giving us the void ratio as a function of dry unit weight here. So it's saying that the E void ratio is obtained by taking specific gravity multiplied by unit weight of water, and we divide this by dry unit weight, and we take everything, we do -1. How do you obtain the unit weight of water? Please, that is universal, 9.81. Everywhere you go, everywhere you are. The dry unit weight, you can establish this, you can get it in your lab. You just need to weight the soil and find its volume. Okay, so by doing that, you can easily obtain dry unit weight, but make sure that your soil is dry, of course. Oven dry your soil, make sure that there is no water in the soil at all, no humidity in the soil. In that case, you put the water in the in somewhere, and by knowing the volume of the water, water, not water, sorry, the solid, your soil, putting the soil in somewhere, knowing the volume of the soil and its weight, you can obtain the dry unit weight. And specific gravity is given by for a lot of soils, you have this specific gravity. So anyway, if we use this formula replace it in this formula of relative density, we can obtain relative density as function of unit weight, dry unit weight. So for that, we need E maximum and E minimum. So this is formula for E, okay? So E maximum, and here you have to be careful, please. E maximum will be obtained with the minimum dry unit weight. Funny, right? The minimum dry unit weight. Because if void ratio is max, it means the weight is less. That's the meaning. Okay. So the Emax will be with the same formula, but using the minimum dry unit weight. And E here, E minimum will be obtained by the maximum dry unit weight. So by replacing the E maximum and E minimum, these two, in this formula, and the E also, of course, we replace them in this formula of relative density, you can get this as formula of relative density using only the dry unit weight. So this one, this is your current, your actual dry unit weight you have right now of your soil, and the minimum one, the maximum one, minimum one, maximum one, and the one you have now. Okay, And do you remember that I told you that everything you have with unit weight, you can have it by using density also. Very easy. So if we go with density, we can say that the relative density also is equal to this one. Check this formula and this one. The only thing we different in this with these two is just this here is gamma and this here is rho. So rho d minus the minimum rho dry, which are divided by this difference, maximum rho dry and minimum dry density. Here, maximum dry density divided by the dry density you have in your lab or in city right now. Okay. So you can use unit weight or you can use density. That will depend on your situation and sometimes your choice. Some people use this one. It's easy. Okay. I will put these two formula here. Relative density using the unit weight, dry unit weight, and relative density using dry density. Okay. So now let's explain a little bit how do we obtain the maximum and the minimum dry unit weight of granular soil. How do we do that? This unit weight, maximum and minimum dry unit weight. And I told you, everything you do with unit weight, you can do it with density also as well. I hope you know the difference. Unit weight is using weight in Newton or kilonewton. But density is using mass in gram or kilogram. Okay, so unit weight is weight divided by volume. Density is mass divided by volume. That's the difference. Okay, so the procedure to obtain the maximum and minimum dry unit weight for granular soil. This American Society for Testing and Material designation, these two provide the procedure for determining the maximum and minimum unit weight for granular soil. Okay. So after obtaining the minimum and maximum unit weight, we can use this formula, these two, to obtain the relative density. Okay. That is the objective. So for sand, which is a granular soil, of course, we use a mold with a volume of 2,830 cubic centimeter. Do you know a mold? Like recipient. So which has this volume. And something like this. You see it? With this volume. So the volume of the mold is known. And the weight also, of course. You can weight it and know the weight. So for the minimum dry weight, which is the minimum dry density also, same time. How do we obtain that? For the minimum one, I think it can be obtained by using just loosely, you just pour the sand loosely in the mold. because we want the unit weight to be as small as possible. So in that case, you don't need to make any effort. You don't need to do any complicated thing. You just pour your soil, your sand, in the mold. Just loosely pour it. Okay? You don't need to do anything. It said here that we can use the funnel of this diameter opening, but I think it doesn't matter what you use. Just pour it loosely. If you use this, of course, this is a recommendation of maybe American, but I'm not sure what you are using in your lab to do it. Just pour the sand loosely, and the average height of the fall of the sun in the mold is about 25.4 millimeter. It means that you don't have to make it too high. Okay, and just the top of your mold is here. Be sure that the height when you are pouring the sun is about 2.5 centimeter. Okay, just don't make it too high. That's the meaning. Yeah, so the value, and in that case, the value of the minimum dry unit weight can be calculated by using just this equation. The weight, if it is full, because you know the volume of this mold already, so just go and weight it, and you will obtain the weight of the soil, and you divide by the volume. We say the volume, you know already the volume of the mold. Okay, do you remember the volume? We just in the previous slide, let me go back and show you. This is the volume. Okay, so if you know the volume, you go and weight also the empty mold. If you weight it, you will know how to find the weight of your soil later. So empty mold, you know the weight, and full mold, if you weight the full mold, you take the minus the weight of the full mold minus the weight of the empty mold. You will obtain the weight of your soil, and the volume also, you know. So in that case, it's easy to obtain the minimum dry unit weight. For the maximum one, how do you obtain the maximum dry unit weight? That one, the maximum dry unit weight is determined by vibrating sun in a mold for 8 minutes. So it means you put the sun and you vibrate it during 8 minutes. And while you are vibrating, you have a sharp charge of 14 kilonewton per square meter. Means on your soil. Okay, for example, if you see this mold, you have this load, the sharp charge. You can put on the top of the soil, and to obtain this 14 kilonewton per square meter. So you add this load on the top of the sun in the mold, the sun being in the mold, and you add the sharp charge on the soil, and then you shake for 8 minutes, and the mold is placed on this the table, and the table vibrates at the frequency of 3,600 cycle per minute. fast, I think. And the amplitude of the vibration is 0.635 millimeter. Means the amplitude means the distance, horizontal distance that the table will move from left to right, for example. Okay, that is the amplitude. And the value of the maximum dry unit weight can be then determined at the end of the vibrating period. So after vibrating, you can then determine the maximum unit weight, because you will know the weight of your soil and the volume of the sand in the mold. Okay, so there are several factors that can affect this, the magnitude of the maximum dry unit weight. These factors include the magnitude of acceleration. Here, the test, the American code is saying, American norms saying that it should be 3,600 cycle per minute, but you can do higher than that if you want. And also the surcharge load. As you can see here, this photo, we have many surcharge. If you put this surcharge, the dry unit weight you will get will not be same as when you put this surcharge. And this big one also, it will not be same. Okay, so another factor is geometry of the acceleration. Here, for example, geometry, it's saying that 0.635 millimeter means the amplitude of the acceleration. Okay, so you can do more than that if you want. You can do, for example, 0.9, it up to your capacity of doing this vibration. But anything you change in this parameter will definitely affect the dry unit weight you will obtain, the maximum dry unit weight you obtain. This is how minimum and maximum dry unit weight are obtained. So when you see maximum and maximum and minimum dry unit weight of any soil, for example, in Japan here we use Toyora-san, maximum and minimum dry unit weight of Toyora-san is determined, they are determined by using this procedure, this kind of procedure. Okay, so you can obtain larger dry unit weight than obtained than by this standard American standard method described, because this American standard method is asking you to shake it for 8 minutes and use a surcharge of 14 kilonewton per square meter, frequency 3,600, amplitude 0.635. So if you can do higher than this, more than this, you can obtain maybe a larger dry unit weight. That is the meaning. Okay, so I think another thing which is not listed in this point is the number of layer you can use. I'm not talking about this anymore, this standard anymore. In your lab, you can decide to use the number of layers in your experiment. Like, don't put the sand, the whole sand at once. Okay, put it step by step. For every step you vibrate with flow. You add more, you vibrate, you add more, you vibrate until you reach the maximum volume. Okay, yeah, you can do that also. So just small exercise before we finish this part, this section 6 of this chapter. The mass, sorry, of most soil sample collected from field is 465 grams, and after over drying the soil, the mass is 405.76 grams. Okay, the specific gravity of the soil solid mean the solid particle of the soil is 2.68. The void ratio is 0.83. So we are asked to find A, the moist density of the soil in the field, dry density of the soil in the field, the mass of water in kilogram to be added per cubic meter of soil in the field for saturation. That means if we want to saturate the soil, what mass of water we should add per cubic meter of soil. Okay. So A, let's go for the mass density of the soil in the field. The mass density, we know that the water content, the moist content is given by this formula. Okay. So omega is what weight of water divided by weight of soil. Weight of water, how can we obtain the weight of water here? And I told you also, instead of weight, we can use also mass. Okay, we can use mass of water and mass of soil to obtain this water content also. So here we use the masses by doing mass of the wet, the most soil sample minus the dry one, we can obtain the mass of water. This is what we did here. And mass of water divided mass of soil, a solid particle, which is here, we can obtain the water content. So here we have 14.6%. Okay. And the dry density now, because here it's not about unit weight, we are talking about density. So we have this formula. This is the definition of the density, mass divided by volume. So by using this formula, we can obtain this density. 1 plus water content, and we multiply by the specific gravity of soil multiplied by the density of water. These two are actually, by doing this, multiplying this by this, you obtain the density of the soil particles, rho S. Anyway, we divide this by 1 plus E. And numerically, when we apply, we obtain this density, 1,678.3 kilogram per cubic meter. And B now is about dry density. We have also this formula that gives us dry density by using just specific gravity, the density of water, and the void ratio. We can obtain easily the dry density, which is 1,464.48 kilogram per cubic meter. And the last one, the mass of water we have to add. That one is easy actually. You just do the density, the saturated density minus the current density, the actual density you have. Okay, so by doing that, you can obtain the density of the water you need to add to obtain saturation. Yeah. So by doing that, such in this formula, you can say that saturated density is you can estimate the saturated density first, and then you use this formula to estimate the mass of water you need. So saturated density is given by this formula. Actually, I don't spend too much time on this formula because we have talked about all these formula in the previous videos. Okay, so these are all known. It's not new. So if you don't know them, I recommend you go back and check this video. And we can obtain the saturated unit weight by this formula and apply this saturated one minus the current um, unit weight, density, sorry, and you can obtain the mass of water per cubic meter, because here actually it's saying to be added per cubic meter. So that's why it is. You can easily use this. So if it was only the mass of water, that would be maybe a little bit complicated. But here it's saying mass of water per cubic meter. That make it easy. Okay, I think that's all for this video, for this part of this chapter. So I think there is just one part of this chapter. We will do it with another video. Okay, thank you very much. See you next time.